All right, so this option is about astrophysics. And astrophysics is broken up into smaller subtopics as well. First thing to understand about astrophysics, basically the study of space and everything in it, is one thing that's really helpful to know is distances of stuff. Like, how do we figure out how far away something is? And instead of using meters, which we're used to, because meters like that long, we're going to have to use other units like astronomical units, AUs, uh, light years, parsecs. So we have to define what those are, and we have to know how to convert from those to meters and etc., and how to measure those distances that are vast beyond our scope of units of measure that we're used to, and how to work with them. So this is a very mathy part of the unit. So let's start with the first unit, which is an AU. AU, how's it going? One AU is defined as the average distance from the Earth to the Sun. And so one AU is the average distance from the Earth to the Sun, which is given by 1.5 times 10 to the 11th meters. So that conversion is given to you on page 2 of your format packet. Another unit of distance, because things are really spread out, is the unit of a light year. A light year is the amount of distance that light travels in 1 year in a vacuum. So light in a vacuum travels the fastest it possibly can go, which is 3 times 10 to the 8 meters per second. Let that light travel for an entire year. How far does it cover? That's 1 light year of distance. That's how it's defined. And a parsec is defined, the symbol for a parsec is PC. That's 3.26 light years. So these conversions are all on page 2 of your formula packet. So they're helpful to know those conversions, but where do they come from and how are they used? So here's one example of a parsec. So if I look at this diagram here, if I, the Earth obviously orbits the Sun. So at one point of the year, the Earth is going to be up here, the Sun's down here. And 6 months later, the Earth is going to be on the opposite side of the Sun. So I look up at the night sky and I see a star. And I can measure like some angles about that star. And then 6 months later, I measure the same angles with the star and it changed a little bit. And I measure it against the background stars. I can see how that star changed relative to other background stars. I can basically create a giant triangle with one known side and one known angle because I can measure the angle and I can use that AU as one of the sides. So here's what it looks like. I got that star and I'm measuring it off of the background stars that are really far distance in the past that don't really change angles. And I can use triangle because if you look at this, this is one AU. And if I draw a triangle here, bump it up, from the star, it's really far away, to the Sun, to me, or I can draw a triangle on the other side, the same triangle. I have a triangle, and I can use good old SOHCAHTOA and trigonometry to figure out some stuff about that triangle. So this side of the triangle is 1 AU. This is, the distance from here to there is at 1 parsec if this angle is 1 arc second. What the heck is an arc second? Well, we're used to using degrees, right? There's 360 degrees in a circle. So 1 degree is 1/360th of a circle. Well, if I take 1 degree and I break it up into 60 pieces, that's a really, really small angle. That's called an arc second. So 1 degree is 60 arcs. Sorry, my bad. Arc a minute. It's called an arc minute. If I take 1 arc minute and divide it into 60 again, that's called an arc second. Think about time. 60 seconds in a minute. 60 minutes in a degree. Well, okay. So an arc second, so 60 times 60 is 3,600. So it's 3,600 arc seconds in 1 degree. You can imagine how small of an angle that would be. So if I look at the stars and I measured the star to move 1/3600th of a degree, that means that star is 1 parsec away, or 3.26 light years. That's kind of crazy. And the closest stars are like 4 light years away. So people that use those telescopes to measure those angles, very, very precise measurements are needed. So let's do a couple examples here, just to think about the scope of how we measure stuff that's this vast. Now, there's other ways to measure stuff too. We can use physics equations to back up our measurements. Like we can use these measurements to kind of like estimate how far something is. But then when we get things like Newton's law of gravitation, luminosity, intensity, and other things, to also confirm those measurements, that kind of reinforces that we have a good estimation of how far away these things are. So let's go through question A. The speed of light is 3 times 10 to the 8th meters per second. It's really fast. Calculate how far it travels 1 year. We know the answer is going to be 9.46 times 10 to the 15th. But how do we get there? How do we get that measurement? Well, we start with this. We have 3 times 10 to the 8th meters per second. So every single second, it travels 3 times 10 to the 8th meters. Well, this kind of works through the math here. So 3, oh my gosh, these markers are terrible. Oh my gosh, yikes. Okay, so 3 times 10 to the 8th meters per 1 second. We want to figure out how many meters it travels in 1 year. So we want to get rid of seconds. Well, how many seconds in a year? You know that's off the top of your head? I don't, so I'm going to convert seconds to hours. So it's 3,600 seconds in 1 hour. Okay, so we're left with hours, how many minutes or meters per hour we would have. Now there's 24 hours in a day, so 24 hours, 1 day. Okay, check. We're left with meters per day, but we want to figure out how many meters per year it travels. So there's 365.25 days in 1 year. Remember, the leap year adds another about a quarter of a day a year, so that's why we have to add a day on after 4 years. But when you multiply 3 times 10 to the 8th by 3,600 by 24 by 365 by 25, you indeed get 9.46 times 10 to the 16th, or is it 15th, my bad, meters. So that's the way to convert meters to light years. Like 1 light year is how far light traveled literally in 1 year. It's that many meters. How many meters are in 1 parsec? Well, a parsec is 3.26 light years. So 3.26 light years, I would literally just take 3.26 times 1 light year, which is that, and I don't know what that is off the top of my head. Let's do that. This is going to be about 3.1 times 10 to the 16th meters. So 1 parsec is 3.1 times 10 to the 16th meters. Now, we just have this triangle here, so we want to prove that this is true with the distances. So using the triangle, 1 AU is 1.5 times 10 to the 11th meters. 1 arcsecond is 1/3600th of a degree. So look at this triangle here. One parsec is defined by this distance here, distance to the star, which is x. So if I look at this, I have opposite, hypotenuse, and angle. It's going to be sine. Sine is opposite over hypotenuse. So solve for x. X would be the opposite over sine. So if I put 1.5 times 10 to the 11th divided by sine of 1 over 3,600, make sure that's in parentheses, I indeed get my answer of 3.1 times 10 to the 16th meters. So it does work out. You can try it out. So that's the first step of astrophysics, is figuring out distances. How do we work with that? That's only part of this first little check-in. So the next part is about black body radiation, which we've covered in detail, but we're going to go over another example with astrophysics. So.